be up from a week from Monday is our goal to have the marks posted, so we can change. And then we'll just lead up to the final. We're almost two weeks left after this. Almost there. Okay. Okay. So. So today we're going to continue our look at improper, as opposed to indefinite, improper intervals, like this one here. This one's a new feature. This one has two infinities running around. New feature. Okay. And because it has two infinite values, that makes it extra slippery, so we actually have to have a way to deal with this that's systematic. It's really easy for infinities to look like they're canceling themselves out, and it's really easy to fool ourselves about what's going on. So we're going to have a rule for this kind of scenario where there's two infinities, and that is to break it into two separate integrals, each with only one infinity per integral. So you must break up into two separate integrals, each with only one. Only one infinity. If either, what we do with this is if either new integral diverges, is the phrase we use, or is infinite, then the original integral is also infinite. That's if either one does, diverges. And only if both of the new integrals converge or are finite, does that imply that the original converges and is finite? So there's nothing shocking here. I'll just copy this down first. The textbook has a lovely box with this in it. All right. Okay. So this is just a way to be careful about infinities, as we know we have to be, because they're slippery things. We can fool ourselves in all sorts of bizarre things like 0 equals 1 if we're not careful with dealing with infinities. And you'll actually have an example in your tutorial next week where you deal with exactly this problem. So this is going to be our rule, and there's lots of good reasons for it. You see two infinities, break it into things so there's only one per integral. And if either one of those new ones is bad, diverges, then we're done. The whole thing diverges, we're finished. If it turns out that both of them are nice and well behaved, then the overall integral is nice and well behaved. So pretty much what you'd expect. Okay. Let's see it actually in practice here. There we go. So in this particular case, how can we break this up? Well, we have the integral out to minus infinity. Okay. And we have the integral out to positive infinity. So what we can do to get only one infinity per integral is just cut it somewhere, wherever we like. I am going to cut it at the completely arbitrary point of x equals 6. That was awesome. Why? Because if it matters where I cut it, then there's something bad going on. If it doesn't matter where I cut it, then it doesn't matter where I cut it. This integral is the area beneath the graph. I don't know what the graph looks like, but I'm asking for this entire area here. If I cut it in two pieces at x equals 6, I should get the same area if I cut it at x equals -2 or x equals 0, right? It's an area. It shouldn't matter where I cut it if I'm going to add up the two pieces once I'm done. That's the weird message right now. So I can cut this wherever I like. Would you rather cut it somewhere else? Yeah. Okay. I just wanted you to know that you don't have to cut it at 0. We always do. It's true. We always do cut it at 0 because it's tidier, it's nice, it's symmetric. But you don't have to. 0 is not a special point if we're adding up the area from -infinity to infinity. It doesn't matter at all where we cut. Okay. So let's recognize what we have here. This is a doubly infinite. It has a double infinity. And so we have to do something with it first. And so we're going to break that up into an integral from -infinity to 0 plus an infinity from 0 to infinity, positive infinity. And this is a single infinity. And this is also a single infinity. And so this is good. In math, as an engineer, we like reducing new problems to previously solved problems. This is something that's new. This is something we've done already. We know how to evaluate it. So is this, and the two things should add up because what areas have we just talked about? We've talked about the areas up to 0 from -infinity. That's that region. And then we have the region afterwards. That region. So we're just breaking our overall area into two sub-areas, which are obviously, when I add them back up together, equal to the original. Okay. Questions or comments before we dive into the actual computation, which will be exactly what you've seen before. This is the new part. All right, then let's take a look. So this is what we want on the left. And we're going to start, we'll do this one first and see what we get. So let's give these guys some names. Let's call this I1 and I2. And we'll do I1 first. Of x squared e to the -x cubed dx. And the first thing we have to do before we begin anything else is what? Must absolutely have to do on any test, or you'll lose marks. What's the first thing you do? Sorry to scare you all. It's a very simple thing to do. It's a very easy thing to do. The limits, right. There are no negative infinities when we do integration. We put them here as a representation, but we have to apply that definition for the improper integral. And acknowledge that it is an improper integral. There's something fishy going on, and we need to be careful how we handle it. So we take the limit as, we can call it whatever we like. We've been calling it t. I'm going to call it a this time. A to 0. This infinity is a problem, or at least a point of concern. It's not a problem. But it's not a number. If I say, instead, what's the integral from some number up to 0 of this function here, that's a reasonable thing to ask. That's a finite area, and then later we can find out what happens to that area as we push our a value down. So if we look on this graph up here, this would be like having an a as a boundary point, and we're going to shift it afterwards. Once we find the area, we're going to push a towards negative infinity and see what the areas converge. Okay. That's the first step. Next step is actually doing the integration. And we'll do that on the next page just for space. Okay. I apologize. I know we didn't leave quite enough space in the notes this time around. I'll try to clean that up for next week. So, limit as a goes to negative infinity of 0 to, of a to 0, x squared e to the negative x cubed dx. I think it behooves us at this point to ask, what's the antiderivative of the x squared e to the negative x cubed? Because that's what all of these integrals will involve. After you're studying, you should hopefully look at this integral and go, what technique will help here? Yes, substitution, absolutely. So let u equal what? Negative x cubed, absolutely. So, substitution here. So du dx is equal to negative 3x squared, or 1 over negative 3x squared, du equals dx. Okay, that's good. And we can then evaluate our integral. It will be the integral of x squared e to the u, and the dx becomes 1 over negative 3x squared e to the u. Yeah. And the whole point of that exercise is that our x squareds cancel. And we're left simply with the integral of e to the u, with u as our variable of integration, with a little bit of tidying with constants. Negative 1/3, e to the u du. That is negative 1/3 e to the negative x, oh sorry, 67. E to the u plus c. That's our antiderivative. And then last but not least, we go back to x's. All right. So also, like many things in math and engineering, we've got a big problem, we're going to reduce it down, and then we're going to take those pieces and build them back up again. So we found the antiderivative of the x squared e to the negative x cubed is this. Now we can use that in our definite integral over here. So we're going to use that to fill in the next line of our integral here. The integral of x squared e to the negative x cubed is this thing. Negative 1/3 e to the negative x cubed plus c from a up to 0. A up to 0. That's good. And we just keep copying this limit. We haven't done anything with it yet. We can't do anything with it yet. We need to get an expression first. So negative 1/3 and everything here. Upper limit first, e to 0 minus e to the minus a cubed. And if you like, plus c minus c. No surprises so far. Just calculations, lots of calculations strung together, but no surprises. What do we get? Now we can say, all right, this is a function of a. If I choose a, I get numbers. Now we can finally ask, what happens to this? This is the area underneath the graph from a to 0. What happens when we push a further and further out? What does this term here converge towards altogether? 0. Exactly. Even negative, large numbers, is going to go, sorry, it's going to negative infinity. Sorry, just having a real flashback here for a second. Let's go to 0. No. Sorry? It's going to go to a big positive number. Yeah, we have triple negatives. Does that make any sense? Hold that thought. This is a new discovery. All right. Oh, it was x cubed to start with. Yeah, okay, sorry. We're good. Sorry. I thought it was x squared. Absolutely. So this thing, yes, yay, this thing goes off towards positive infinity as a approaches negative infinity? It does. Okay, let's pause there for a second to make sure we all agree on that, because this is something that might not be obvious to everyone. In fact, probably is not obvious to everyone. Imagine if we put in negative 1 million. Just a little mental experiment here. Let's say A is large and negative. Then we'd have e to a negative value, that's a negative large thing cubed, and that's e to a large thing cubed. We'd have all these things, all these signs cancel out, we have a big positive thing. So e to a large number is big, and then we cube it, it gets bigger and bigger, and it's positive. And as this number gets bigger and bigger, well, this exponential is going to get larger and larger, and so on. Does that convince everyone that it actually goes towards infinity? Or better yet, is there anyone who's not convinced that it heads off towards positive infinity? Do a quick show of hands. How many people are comfortable with this statement? Excellent. Okay. Well, the nice thing about this is we just saved ourselves a whack load of work, because let's go back to what we said about this rule. That integral exists and is defined only if both of the new parts converge. We just said that one of them, this half here on the left, blows up. The area underneath there is not bounded. It goes off towards infinity. So what does that mean about the overall integral in the top corner there? It must go off to infinity. Exactly. It doesn't matter what happens on the right-hand side. We're not going to let cancellations happen. If this side here is infinitely large, then things are poorly defined, things are undefined. We can't say there's an overall value. So just by that one step of finding one of the integrals diverging means the overall integral diverges as well. So I1 diverges. And that means by our rule from a couple of pages ago, the overall, or the original, integral also diverges. We don't even have to look at the other half, because the only way for it to converge is for both to converge. As soon as we get one failure, the whole thing is failed. Perfectly valid answer, diverge. Questions, comments? So the answer is most appropriately is divergent rather than equals infinity. It covers the whole. Divergent is the umbrella organization over all the infinities, doesn't really go to something finite. But yeah. Can't go wrong with divergence. Yes?
Any way to tell which half by which is the left or right integral?
Good question. So that is an excellent question. Let's go back to statement of use. Lost there. Right. So if you're trying to be efficient and trying to identify how, if you think it's going to fail, so that's the first thing. If you look at the integral, you think maybe the area is infinite. I would definitely have focused on the left-hand side for this integral for one very good reason. Just think of the graph of e to the negative x. What does that look like? It's a decaying curve, right? Well, it turns out even x cubed is going to look the same, basically, in shape. Negative values, when you cube them, are going to become positive. You're going to have big positive values. So in fact, if you just ask what's the area underneath the negative x cubed on the left-hand side, it's going to be infinite, the graph keeps going up. Of course it's going to be unbounded. I throw in an x squared, it just gets worse. It's actually, the function goes off towards infinity really fast. So the area underneath it is clearly not going to be well defined. So I'd focus there. If it had been positive x cubed, it would be the opposite scenario to the other one. Honestly though, the actual time difference is minimal if you choose the wrong one to go first, because this is what takes the time. This part's really easy. Integrating it all is what's going to consume most of your time and effort, so you'll have to do that either way. So it's not a big deal, not a big difference if you choose to do one first than the other. Okay. If that's okay, if that feels comfortable, it seems like it did, we're going to then tackle our second type of integration problems or improperness that can appear, and this is one that people asked about last class. What if our integrand goes off towards infinity? In other words, the infinity is not in the x direction, but there's an infinity in the y direction. So there's still some dimension that is growing unbounded. Here's a classic example. The integral from 0 to 1 of 1 over x squared. Note that 1 over x squared is not defined at x equals 0. So that x equals 0 in the bottom end of our integration interval is going to cause a problem. There's something improper about it. So this would be another type of improper integral. Okay. Let's take a look at this and just remind ourselves that this area over here, this area out towards infinity, or x approaches infinity, area as x approaches infinity is finite. We did that last class. We said, hey, if I have 1 over x squared and I go out this way, the function seems to shrink fast enough and the area underneath the graph is limited somehow. We're going to see that's the opposite scenario if we blow it up if we go towards this asymptote, we're going to see the opposite. The technique is going to be exactly the same. All right. We're going to use a limit in the same philosophy as before, but the technical detail is different. What we're going to do now is, we are going to define a new point A, and we're going to talk about the area from A to 1. And the whole point is that the area on the interval A to 1 will be finite. And so what we're going to have here is A is to the right of the asymptote. It's going to be a little technical thing we have to be careful with. We'll see how it plays out. I think it'll make sense once we see it. So the idea is instead of asking what's the area underneath the graph from 0 to 1 when we have the asymptote included, we're going to say what's the area included from A to 1, which is a perfectly valid, nice integral like we've seen before. And then we're going to push the A value closer and closer and closer to 0 and see what happens to the area as we do that. Exactly the same procedure as when we took our T and pushed it out towards infinity. The only literally little thing to add here is a direction. So we have the integral, in this case here, 0 to 1 of 1 over x squared. This is an improper integral because of that asymptote. Because of that, we have to use our rule to handle the asymptote, and that's we're going to take the limit as a goes to 0 of 1 integral a to 1 over x squared dx. So this 0 is our bad point, our suspicious point. That 0 down there is our suspicious point, and we're going to replace it with a real finite value that's not 0, and then we're going to push a closer and closer to 0, and the only little technical tidbit is that there's going to be, sorry, space here, from the right. This 0 plus here means from the right. Why do we need that? Because I don't want my A value to be on the far side of the asymptote and then be pushed towards 0 because I don't know what the area with the asymptote is yet. I can't include the asymptote. So we always keep A on the right and push it down towards 0. In terms of the limits you do, it makes no difference in almost every case. This is the correct form because it actually means that this is a finite number, and then we're seeing what happens as we push the boundary. Okay. But what I want you to take away from this, the most important thing is, this is a bad point. How do we handle the bad points in the integral? We say a limit, and we get closer and closer to that bad point while using some other boundary that is a good, perfectly valid limit of integration. Questions or comments before we do the calculation? Let's do the calculation then. Excellent. Integral from 0 to 1 over x squared dx is equal to, that definition, the limit as a goes to 0 from the right of a to 1 over x squared dx. And same as before, copy the limit, we'll do it, we'll evaluate that limit last. Focus our attention on the integral. Antiderivative of 1 over x squared is what? Negative 1 over x. Absolutely. This is better known as x to the negative 2. The integral of x to the negative 2 is x to the negative 1 over negative 1. Or negative 1 over x. We will evaluate that at 2 points. 1 and a. So there's our antiderivative. Then we're going to sub in our limits. A and 1 for the boundaries. And we just keep copying this a goes to 0 in front. We're going to get negative 1 over 1 minus negative 1 over a. That's it. And we'll say plus and plus, sure. And now we can ask what happens if a gets larger, or gets smaller. Sorry. What the effect of a going to 0 is. We try to plug it in. Hey, I want to find out what the limit is as a goes to 0. I'll try to plug in 0. Good thing or bad thing? You have 1 over 0. What's going to happen to this term? It's going to blow up. It's going to be infinitely large. And that's what we actually would have graphically, is that this area grows unboundedly and the integral diverges. The 1 over a term goes off towards infinity. So our integral diverges. So the integral from 0 to 1 of 1 over x squared dx diverges. Does not go to some nice finite value. All right, questions, comments, thoughts? Let's do another one then. Okay. Perfect. What could be more fun than that? All right. So having done your partial fractions last night, this should be familiar. You should look at this and go, hey, maybe partial fractions might help. So let's take a look. Let's say this is equal to the integral from 0 to 4, 1 over x plus 3, 1 over x minus 2. Why is this an improper integral? Doesn't look like it. There's nothing that says, hi, I'm an improper integral unless you look carefully. But it is, and why? Yes, do that. Asymptote at x equals 2, or yeah, the negative 2 causes an asymptote. Exactly. At x equals 2, this function is called the integrand. The integrand is undefined. That's a problem. We have to do something about that. So what we have in terms of our limits of integration is 0, 4, at 2, the graph does some kind of presumably asymptotic kind of thing, and we're trying to find the area underneath the graph between 0 and 4. Well, that's a bit of a frustrating thing to have to do. What can we do to focus in on the problem area? No. Absolutely, we can split it into two integrals, because look, we actually have two problems. We have a problem from 0 to 2, that could be infinite. And we have the area from 2 to 4, and that could be infinite. Oh, if we have two infinities, we should split it into two pieces, and look at each piece separately. So, we're going to have to split this at the asymptote. That'll be the integral from 0 to 2 of 1 over x plus 3, x minus 2 dx, plus the integral from 2 to 0, or 2 to 4, sorry, the same thing, dx. So we have one integral over this range, and then we have a second integral over the second half of the range. And we confirm that these both have a single infinity in them now. That's good. The 0 points, unlike the last case, plugging in 0 into that formula is fine. Got no problem with 0. 2 is a problem because 2 minus 2 is 0. In the denominator, that's what causes the difficulty. Okay. So we've reduced it to a previously solved, or at least understood problem. So let's take a look at each integral separately and see what they evaluate to. Again, both of them must converge if the whole thing is to converge. Now, I'm going to save us a bit of time because the partial fractions, as much fun as it is not the most exciting part. Okay. Awesome. All right. Guess we're going to partial fractions. All right. All good. So if we want to decompose 1 over x minus 3, x plus 3. What should this be equal to? There we go. Yeah. Or multiply that up. 1 equals a, the x plus 3's cancel, we get x minus 2, the x plus 5. This is true for all x, so we can pick our convenient x values. And we'll have a times minus 5. There we go. If you want to save yourself some copying, this is going to end up being infinitely large. It won't matter what you copy down. So it doesn't ruin the surprise. Alright. So the integral, I1, is the integral from 0 to 2 of 1 over x plus 3x minus 2 dx. And that is equal to, by the definition of improper integrals, the problem spot was the 2, so we have to take the limit, and you can pick whatever variable you like as long as it's not x. I like a and b. That's my personal favorites. If I'm going to do an upper limit, I like picking b. To 2 from the left, because we're going to go from 0 towards, up from below towards 2. 2 from the left, up to b from 0. And I'm going to do the other thing as well. We'll do the partial fraction at the same time. That will be a was negative 1/5. 1 over x plus 3 plus b, which is positive 1/5, 1 over x minus 2. So 2 things. The 2 is now a b, and we'll let b approach 2. That's the improper part. And the 1 over is complicated, so we use partial fractions to break it down into these two separate components, which we can now integrate directly. Let's do the integration then. Actually, let me pause for questions. Any steps in there causing concern, trouble, difficulty? Turn it on. Good. Okay. So the integral here, bring it up top, is the limit as b goes to 2 from the left. Integral of 1 over x plus 3. Ln, yes. So we'll have negative 1/5 ln of the absolute value of x plus 3 plus 1/5 ln of the absolute value of x minus 2. All of that between b and 0. And you'll see now why we need our absolute values, because x minus 2, when we plug it into 0 values, would be ln of negative 2. That wouldn't make any sense. But it's perfectly valid with the absolute values. So limit as b goes to 2 from the left. Negative 1/5 ln of b plus 3 plus 1/5 ln of b minus 2. These should be absolute values again. All that minus a bunch of other stuff with lns and zeros. Why am I waving my hands at that? Because we have the problem right here. B is going to 2, and we're having the ln of b minus 2. What happens to ln as you plug in values closer and closer to 0? It goes to infinity. Exactly. So this limit here heads towards negative infinity or diverges. So the overall integral diverges. Same thing as last time. So I1 diverges, which implies the original integral from 0 to 4 of whatever we had, x squared plus x minus 6, also diverges. That's it. Okay. Now someone might ask, wow, we don't really come across infinities very often in real life, do we? Why are we wasting all this time looking at infinities? I do want to show you at least one glimmer of where this might show up. Physics. Physics, you blame the physicists. The physicists and chemists have infinities everywhere. They love them. Imagine a point charge out of infinity being brought closer to one. Like, that's what they love. We're going to look at it in a gravitational framework here and show you where you might actually need an infinite integral. In fact, we've already looked at this kind of scenario. We're going to imagine the force that it takes to take an object and move it away outside of the gravitational field. So here we have the Earth. And we're going to take some object and lift it away and away and away and away and away. And the idea is that we should be able to calculate a whole bunch of different properties. The one we're going to focus on today is called the escape velocity. Who here has heard the escape velocity? Raise your hand. Excellent. Can someone define the escape velocity for me? Can one person define the escape velocity for me? Roughly, huh? Yeah. The speed you need to be traveling to escape the Earth's gravitational field. Exactly. And when we say escape the gravitational field, how far does the gravitational field actually go away? Hey, there's our infinity right there. So that's it. That's why we need these infinities, because these fields go on forever. So how do we sneak up on that? Well, we're going to need force times distance equals work. velocity for some object on the Earth, we have to consider the energy. The energy is the easiest way to do it. Conservation of energy is our friend in physics. We're going to imagine moving an object out by little units of, when we talk about r, or the radial distance from an object to the center of the Earth, we're going to use delta r's instead of delta h's, because that's how we typically talk in astrophysics terms. And that's going to give us an integral of our, let's go back a second, big G. Big G m1 m2 over r squared dr. We want to add up the force times a little unit of distance. And we notice that the force changes as we move further away. Of course, we have less and less work to do to fight gravity when we're out past the edge of the solar system. We have a lot of fighting to do when we're here. And that formula will take that into account. As we move and change our radius, our force will decrease and we'll have to do less work. What we want is to go out towards infinity. Where we want to start is at the surface of the Earth. And so that means that r naught is equal to the radius of the Earth. So this calculation gives us the energy to escape the gravitational field. Energy to escape gravitational field. Because of that infinity. The field goes forever, so we say, well, what if we could push it out all the way out towards infinity? And it turns out that this is a really simple integral to do. First of all, we use our definition. We say we want the limit as we bring our spaceship, our object, to some big distance, let's call it b. And then b is going to go out to infinity. M2 over r squared dr. So that lets us handle the, hey, how much energy would it take to move an object from the surface to 5 miles up, to 1 billion kilometers out? That's what we can vary, and then we're going to let that upper limit go larger and larger and larger. Next step is just to recognize that these are all constants, so copy them. The integral of 1 over r squared, pretty similar to the integral of 1 over x squared, is negative 1 over 1r between b and r0. And then we can't forget out front our limit as this upper value is going to get larger and larger and larger. So we copy that across. And that equals gm1 m2 negative 1 over b minus negative 1 over r naught. Sub in the b, sub in the r naught. And now we get a nice, I hope, answer. What happens if b goes towards infinity when it's in the denominator? This term goes to, altogether, 0. Ah, how nice is that? That's so nice because, yeah, I'll put it in the next page. As b gets bigger, we have 1 over bigger and bigger numbers. That's a small number. And so we end up with positive 1 over r naught. So we get equal to gm1 m2 over r naught. That's how much energy we need to escape the Earth. Gravitational field. Cool. So we've done the integral. That integral out to infinity gave us a nice value. And do a quick calculation here, how much energy that actually is for a person M2 is big. The Earth is a pretty big place. 124. Times G, which is really tiny. And we're going to divide that by the radius of the Earth. Okay, that's not the exciting part. I'm going to take 1 more minute of your time. 1 more minute of your time. Because that's not the escape velocity. 1 minute, I promise. Let us see what we can. This number is meaningless to most of us. How much is 4 million joules? I don't know. Oh, sorry, it's not even millions. 10 to the 9. It's actually 4 point. I think I missed my decimal place. Billions of joules. Billions of joules. How fast would you have to move to get that much energy in kinetic form? How would you know the speed?
11.8 kilometers per second.
All right. That's your 4.4 times 10 to the 9 joules is 1/2 mv squared. Your velocity ends up being a staggering 11 kilometers per second. 11 kilometers, like from here out to the 401, actually further than that, in 1 second. All right, thank you very much.